with our first talk. It's Christos about Apache Ignite. It will be a short talk, about 30 minutes, because he has to catch his flight. So, Christos, it's your stage.
Thank you. This mic is working, is okay. So, good to see you guys here. Hopefully we made it. We didn't make it yesterday, but we made it today in the morning. So basically I'm Christos. I've been working in for GridGain actually. I've been working there for just over a year now. I've been in the space of kind of in-memory computing for a while, about 5 or 6 years already, with kind of previous kind of jobs working in similar companies. So ideally what I like to present today is kind of present Ignite, what it is, what it's about, what we kind of use it, what's different use cases, and kind of give you a rundown of the different features that it kind of has and how perhaps you could just give you an idea or inspiration on how perhaps you can use it. So yeah, like I said, we're going to talk about the Apache Ignite project, what's it about, what's the relationship between GridGain, what do we do with the project, and then more kind of in depth about the platform. There's kind of a few distinct features or groups of features, I would say. So we'll talk about a few concepts, so how it works, what the fundamentals are, and then delve into the in-memory data grid side of things, how we could do some processing around there, and then of course have a look at the compute grid, the service grid, and some streaming aspects that we can do. Hopefully, I mean, I've got also HardOOP and Spark integration in there. Those are a couple of slides that talk about our integration with HardOOP and Spark. If you're interested in that one, we'll see how the time goes. I'll try to run through the slides, hopefully, not rush too much, and if we get some time to do that and then get some questions in the end, that would be great. Okay, so yeah, what is Ignite? Pretty much the best kind of explanation I'd like to give is the puzzle is a really good picture. I think it describes a lot. So what it's trying to kind of demonstrate here, it's more of a platform. So it's a group or a collection of different features that all share one common thing. They all work in memory, and they all fundamentally work to give you high performance and distributed computing. So that's about kind of transacting on large data sets in near real time. So and we'll talk a couple of use cases and how that works. So, but as an idea, what it is, it's different features, all built in memory or using in-memory kind of technology to be able to service very kind of high performance use cases. Okay, so the Apache Ignite project. So the kind of the history here, or what really happened, is basically back in 2007, we have two fellas came out of Russia. They moved to San Francisco. They built kind of a grid and what was a distributed compute grid. So that's the idea, to be able to execute different jobs on a group of servers. So that was the initial kind of deployment or implementation of Apache Ignite and what was called at the time GridGain. So these were called GridGain at the time. Fast track that about 2014, after adding a whole lot of features that we're going to talk about, we basically took the product, we open sourced it, gave all the code away, and we created what is called Apache Ignite. So exciting project. So there's a couple of things around that. It's a mature code base, right? It's been around for quite a while. We've had a couple of, not a couple, but a significant number of professional engagements and enterprise users that are using this. So the code is really good. I mean, and the numbers speak for themselves. I'm not sure you can read the text there, but I've just taken this from OpenHub. I did a comparison of what I did in 2016 because I had this slide before. But the whole idea was just kind of to show how active the project is now in the open source community, right? What's important there is it was the second fastest project to graduate after Spark. So Spark is quite a popular technology. We see it around with data scientists and a lot of other use cases. So I think it's quite impressive to see the same kind of momentum behind another open source project. I wouldn't say that we live in a similar world, but we cater for different types of use cases. And you can see there's a couple of numbers there. There's a growing number of contributors, so it's moving forward. There's a lot of activity. There's a lot of interaction with the community, and of course, feel free, join the user list, join the dev list, join the discussion. There's a lot of stuff going on if you're a coder and you enjoy these kind of things. Of course, there's all these simple tickets that you can take on board and be part of the project as you want. Okay, so I mean, what is this thing? What do we use it? What are a couple of use cases, I guess? So I've seen the stuff that we generally kind of focus on commercially with GridGain around the technology that I've seen is usually around fintech and financial services. Those are the guys that really kind of demand these types of technology. So usually you get like automated trading systems or high frequency trading systems, reconciliation engines, risk calculation engines, all the kind of stuff that you get front and back office as well. We've also got other verticals as well that you can use Ignite, and you'll see how it fits in a lot of different things. Online gaming is another one. Doing I know of a use case of doing the leaderboards. As all the data comes in, and then we have to calculate that in real time. Travel and e-commerce is another one that I've seen a lot lately. So that's kind of doing real-time search engines or real-time pricing grids of different reservations, let's say, of hotels or flights or different comparisons that you want to do. So that's all about kind of having the ability to execute a search on a cluster that's big, and also have the ability to linearly scale that cluster as more mobile phones and more users get online and start to use these services, right? And of course now, more kind of recent, I would say, is we're moving more into the big data world. So I think that's there's a lot of stuff being added, stuff that's on the roadmap that will align there. So one of the things, of course, is having the ability to use our SQL engine to query this data, which aligns very well to kind of big data. And not only that, we're now adding, if not already added, I'm pretty sure in Ignite 2.0, we've got the machine learning libraries, similar to Spark, and of course we're extending that as version 2.1 comes out. So, and all you see, like I said, this is a platform and it's a collection of features, so it's not about using all of them, it's about picking the right mix for your use case, right? So what is GridGain and what's the relationship right now? We gave our code away. What do we actually do? A lot of time, we spend evangelizing about Apache Ignite, talking and preaching about it and sharing the technology. But as a commercial entity, what we really do is pretty much provide an enterprise build of Apache Ignite. So if you're going to move into production, you want to really take this into the next level, mission critical applications, which is really what we're geared for as Ignite, then that's something that GridGain can support and provide you with these builds. Of course, there's a couple of different components in the enterprise edition that we'll talk, which basically are more catered for the enterprise, like big data, cross-site replication, added security, added auditing, and stuff like that. So the whole idea that you get behind it is you get a group of experts, that created Ignite, that are still maintaining Ignite, and that can help you drive your project into production and manage it as well. Okay, back to the puzzle. I like this kind of picture. So I think what I try to kind of demonstrate here is just, have a couple of pop-ups from each of these, let's say, pieces of the puzzle and explain a couple of the stuff that we see. So like I said, you're not meant to use all of these at once, but it's kind of a combination perhaps. So usually with a data grid, you would see stuff like, web session clustering. So I've got a number of servers, I've got a number of users accessing this, they have their cookies. What you can really do, for example, with Ignite is use it as a distributed caching layer to store a shared session cookies across and be able to access that from any server. So you don't need to have sticky proxies as your connections come in, right? One use case. Of course, you can also use it for caching requests and responses when you're building, let's say, a REST API or some sort of service that you want to expose. And if you've got a backend database, let's say, and you need a faster way to do that, then using a cache would certainly help. Again, in-memory SQL. So now it's getting a lot more popular, kind of the ability to have in-memory databases, and that's for the reasons of pure speed, right? So again, the SQL API, that's something that you can do with the data grid as well. If I move on a little bit onto the compute grid, so that's your traditional kind of use cases of high performance computing. So different jobs come in, like mentioned before, risk calculations engines, or pricing grids that you want to do in real time, risk analysis and stuff like that. Service grids, so that's pretty much the ability to run what you think of services now, but in memory, right? So you can have a client and a server, and you can have your interface and your implementation. We can do exactly that or follow that exact paradigm, but handle it in memory and add some resilience on top of that and scalability in real time. Streaming, so like I said, that one mostly aligns into big data. That's about having the ability to ingest streams of data into the grid and then process it in real time. The bottom bits of the puzzle, I think it's slightly not, I wouldn't say not interesting enough, but I think it's slightly more low-level stuff that you would use in your implementation. So clustering, that's the next kind of slides we're going to talk about, which is basically how the nodes configure, how they create this distributed platform or fabric. And we also have an in-memory file system that you can use, again, or messaging between the nodes that we can communicate, or even triggering certain processing or certain business logics with the trigger of different events. And of course, data structures, that's kind of more low-level Java structures that you can use for different ideas that you have in your architecture. And we'll get into more detail in each of these. Okay, so let's talk about the clustering. So what it is and how does it kind of work out? So think of it as a collection of nodes, so actually that pretty much cluster together, and they provide you with pretty much a distributed data store. So that could be key value access, it could be SQL access, it could be transactional access. So what we can do in Ignite is take data, distribute it across servers, partition it, or replicate it, however you will, and we'll talk about the different modes, and then provide you with different types of APIs, very flexible APIs for you to access and process that data. And the whole idea of Ignite is keeping this data in memory, where is the fastest place where you can process the data, and also accessing it in the most flexible way, right? And not only that, but also processing it with the right approach, which means as we go into the compute grid later on, you'll see it's all about sending the processing to the data and not actually reading the data and doing the processing. So it might sound like a database or a distributed store in the beginning, and that's what usually people start to use it as, but once you understand the processing or the computing framework that runs on top of Ignite, that's when you really understand how to leverage this technology. Okay, so got some definitions here, and I've already thrown a couple of these different words around. I've mentioned cluster. So whenever I say kind of an Ignite cluster, that's pretty much a group of Ignite nodes. So as we start up, that all kind of work together to accomplish these features, right? So an Ignite node is pretty much a Java process. It runs in the JVM, right? And all it does, it starts up. There's two kind of concepts, what we call an Ignite client and an Ignite server. And these are exactly the same process. Many of them can live on the same server, right? Or even in the same JVM. So a lot of the times you can start up multiple Ignite nodes within the same JVM to test your topology, right? So imagine this can be a distributed grid or a distributed cluster of nodes. Having the ability to test locally and deploy this locally is very important, for kind of as you kind of increase momentum to go into production. Having to test on remote servers and starting that can be a real pain. So like I said, the same idea with Ignite nodes, clients and servers, pretty much exactly the same process. The only difference with a server is that it can store data. And when we say store data, imagine like a distributed hash map or a container that can store some entries, right? The difference with a client, it cannot store entries. So it can access a server and access those entries and read them and do some processing, right? But not really store any data. Both Ignite clients and servers can participate in what we call computing. So when we mentioned the compute grid and processing that, right? So either of these kind of two processes, which are very similar, can execute these jobs, as you will, or tasks that you issue. Yeah, so you can understand there's a kind of what's important to understand here, and perhaps the picture is a little bit deceiving, is like I said, the clients and the servers, they all join the cluster. So what's important there, if you want to build, let's say, a service here, is that accessing your client, is that your client is already part of the cluster. And any topology changes, so any server that leaves the cluster or any client that leaves the cluster, everyone's aware of this. So everyone, all the nodes in the server, all the clients and servers in the cluster, we call them, they are topology aware. So any changes, and this is important because once we move into data partitioning, and it's very important to understand how your data moves around and how you process that. And that aligns very well when we said, how do you actually process your data in the best way? Okay, so I'll move into the kind of the most fundamental piece, I would say, of the feature sets, or the range of features, which is pretty much the in-memory data grid, right? So there's the ability to store the data and access it, like we said. So what does that look like? So imagine we have 4 nodes, right? 4 machines, or 4 nodes that are started on my same machine. There are 4 server nodes, and I want to store some data. The first mode that you can use is what we call a replicated cache, or a replicated data set, right? So that means every node in your cluster, or every server node in your cluster, will have exactly the same piece of information, right? So imagine like a SQL server or a standard database that we just replicate, and you can have access to that data on any server. This could be great for read-heavy use cases, right? So imagine the scenario when I said before about the travel industry, where you want to do like real-time search and very fast search. Usually the data is going to be minimal, it's not big data. There's the working data set that you work, which are the hotels and the availability, for example, and the flights. Usually that data can be replicated. So that's a good idea, where you can have a fully replicated cache. So every server that you add, or every new node that you add, pretty much you get a replication of that data set, and then you increase your capacity by X by adding this server, right? The other mode that you can run is what we call a partitioned cache. And if you've kind of worked with other kind of distributed databases before, like Cassandra and stuff like that, you will understand what the partitioning works like. So the whole idea here is that we split the data set. So in this scenario, if I have 4 servers and I have a distributed partitioned cache, what will happen is each server will get a portion of those keys, right? So if I had, let's say, 20 keys that I want to insert, or 20 rows, if you want to imagine in a database, each server would have 5 of those rows or 5 of those keys. If I wanted to access that through a client, what will happen is when I request key 1, the client request is redirected to server 1. If you want key 2, for example, it will go to server 2. If it goes to key 5, it will go back to server 1. So what we do is almost like a round robin. So that's the distribution of the data, or the way we partition the data. This is fully pluggable, and of course, if you've got usually you don't want to change it, and you want to stick with the default, which is the partitioning strategy. But if you do and you want change it, then there's a lot of these options. What we can also support is a near cache. So remember, as we have these on the data on the server, a client can deploy a near cache. So I know I mentioned before you can't store data on the client, but you can create what we call a small near cache, where some of that data is pushed to the client. You operate locally with the client application, and then any data changes are reflected directly to the server, right? So that's really helpful when you want to push stuff downstream, right? So perhaps rather than having to pull or read from the server, you want to operate locally, and there's third-party systems or other users changing the data, and then you get a push notification of that. So the one thing you're probably going to ask, and I didn't mention here, is there's the concept of primaries and backups. So all this time I was kind of talking about the primaries. The idea there is that you can specify for every key an amount of backups, right? So there in this picture, I've got a one-on-one representation. That means for every primary key, I have one backup key. Now what will end up happening is that backup key will end up on a separate server, right? It will not be on the same node. So imagine a scenario where I lose any of these 1 servers, I still have all my data set. So what will happen in Ignite in real time is once you lose one of these servers, you have what we call real-time rebalancing, right? The data is going to move around, and it's going to rebalance, and then now you have three nodes to work with. You reduced kind of, let's say, capacity, but still no loss in data set. If I lost 2 of these servers in this scenario, I would lose some of my data set, right? Because I don't have that enough backups. If I had 2 backups for each node, then my redundancy goes up. The thing is there to keep in mind that, of course, as you add backups, you're duplicating your data sets, right? So that's how it works. What is important here is the real-time scalability and distribution or rebalancing of the cluster. So you can remove a cluster in real time and still have availability. So, I mean, if you're familiar with the CAP theorem, which is consistency, availability, and partition tolerance, the idea is you can only pick 2 out of the 3, right? So if you want availability and eventual consistency, then you can do that in Ignite, right? So you can have it to be highly available, not block any access to the cluster, and do real-time rebalancing. If you're working with transactional data and you really care about having firm let's say, data consistency, then what you can switch on is the transactionality and drop the availability for data consistency, right? So what that will mean is if a server leaves or a server enters and there's rebalancing happening in the cluster, then the cluster access is blocked from any clients to make any changes until the rebalancing complete. So the main idea or the main thing to take from this is that you can be as transactional as possible and consistent with the data as possible, or you can be as flexible as possible. Always, the more consistent and the more you tighten it up, the slower you get, I guess, or the more you degrade in terms of performance. The more you loosen it up, the faster you go. So that's the main key point I would say here. So, and the ability to split your data into different modes, partition it or replicate it. And of course, you can have a mixture of these caches, right? So you can imagine a cache as a table, as you will in a database. And you can have a mixture of replicated caches or partitioned caches. Okay, so, I mean, we did say we're a JVM-based kind of technology, so you would assume we use the heap. That can be problematic with GCs. Fear not, we have what we call the off-heap implementation. So that's the ability for us to manage through Ignite the data outside the JVM. So this can be very helpful in terms of GC spikes. And we're talking about big data sets, right? I was talking about like last week, actually this week, we're in Madrid working on some stuff. We're talking about 3 terabytes of memory, right? So that's a lot of data that we have to work with. Having to run that in the JVM, that will require a lot of JVM nodes, and you cannot go beyond a certain heap size without having problems. So off-heap can really help in that sense, right? And that's the default version. So from Ignite 2.0, default mode going forward is off-heap. I know you're going to say, what about serialization costs and stuff like that? That's all handled. Once you start getting into Ignite, you'll understand there's some concepts of what we call the binary marshaller, or the ability to keep data serialized already. So we do not keep any classes on the server most of the time, so you can operate basically against a map and a serialized map with that data. So you pay the serialization cost on the client if you need to. So the one thing I probably didn't mention is the ability, we say here, of heap indexes, but once we store data in memory, remember we also have the SQL API, and I'll talk about that in just a moment. That's basically, you can also have indexes that live in memory, and indexes can not only just live in the JVM heap, but they can also be off heap, right? So data center replication. So this is a GridGain Enterprise kind of feature, just to give you a kind of a sense what's in the commercial edition and whatnot in the open source. So that's the ability, remember, of clusters that we described right now, with range of partition caches and replicated caches. What if you want to do that across data centers? That's something that you can get with GridGain, what we call the DR replication plugin, which will allow you to replicate your exact topology over to somewhere else. Or another data center. What you can do is control how this replication happens, how conflict resolution happens, how network split scenarios occur. There's a lot of funky stuff that you can actually leverage in there. So external persistence. We did say we're in memory and we store stuff in memory. So the idea there is you're probably going to say, okay, what if I switch it off, I'm probably going to lose all my data. What you can do is actually integrate with an external persistent store. And that's the ability to have read and write through. So usually what we have in a lot of our deployments is we'll have a lot of historic data, a lot of long-term data sitting in the database, and a lot of warm data or hot data sitting in the cache or in memory, right? So that's the stuff you want to, the most recently used data that you want to operate against. You don't want to waste all your memory to serve data that's not used so frequently. The memory can be expensive, although it's cheaper nowadays, right? Another use for this is the ability to basically recover. So you want to restart your grid and you want to reload your data, you bring it off the database. And the database can be HardOOP, can be Cassandra, can be Mongo, can be an RDBMS or any other kind of JDBC, let's say, interface. If it's something custom, then you can always implement a custom cache store interface and hook it up with your own kind of stuff. And what's nifty here, if you're using a RDBMS, there's a nice nifty little mapping wizard that basically will connect over JDBC, extract all the tables, configurations, create the relevant POJOs, and then create the connection directly with Ignite. So you would operate through Ignite rather directly to your database. So the idea is having an easy way to just slice Ignite in between without having to have too much code change. So cache APIs, how do we actually access the data? there's a range of stuff, like I said. I think this is one of the key points of the technology, is the number of ways that you can access this data. So you can have scan queries. That's pretty much, when you issue a scan query, we scan every row of the data with a certain predicate that you give. Let's say, salary over 1,000 or something like that. We evaluate the predicate for each of those rows. So it can be quite expensive, but a lot of times you need to do some full scans, right? You can do text queries. So if you're familiar with Lucene and Lucene style indexing, that's kind of something that's used behind the scenes. So you can do full text search on the keys and on the values, right? So you can do a full search there. You can drive this configuration or this schema through annotations, so you can plug them into your Pojo classes, or you can use XML configuration to do that, or you can even use a Java config whilst you're starting up to configure this stuff. SQL queries, so that's really important. That's actually something that we're really investing in, and that's one of the, you can never be fully SQL compatible, but we are ANSI 99 SQL compatible, so you can usually execute most of the queries that you're running with a standard kind of SQL database. You should be able to just execute them in Ignite. And actually, what we've well, I'll leave it for the next slide. What we've got is we've got all the aggregation support, so group bys, filters, sorting, cross-cache joins, distributed cache joins, distributed non-collocated joins. So all that stuff is really supported and very fast. And not only supported, like I said, it's growing. It's one of the important investments that we're making. And there's a couple of other interfaces, like you can connect via a REST API or a Memcache client or a JDBC driver, right? So you can just access the in-memory stuff with a JDBC driver. So rather than using the native APIs, another one, that recent addition, and that's because of our SQL kind of feature set, is the ODBC driver, right? So that's really cool because you can use something like a BI tool and just connect straight to the grid and visualize your data that's coming in. So you can use like Tableau or Click and stuff like that to access the data. Okay, so SQL support, a little bit more, like I said, I think we've covered most of the stuff here. What's important is we've added DML and we're adding DDL. So that's basically right now you can do everything in terms of reading data through the JDBC and ODBC driver and directly. You can do modification, but you can't do creation. So there's a slight bit that's missing right now, and that's what we're working on to add by the end of Q2 actually in Ignite. So the idea is there that you should be able to operate against Ignite or your in-memory data set without having to write any code really, right? And just go through the ODBC or JDBC driver and do exactly what you were doing with your database. So, okay, so SQL API, like I said, one of the strong points. The other one that's really strong, I would say, and technologies, if you want to compare it with other competitors out there, SQL 1 and transactions would be the other, right? So come from a very strong, consistent background in terms of data consistency. So you can have fully transactional or atomic operations. These can be cross-cache transactions. So remember, if we have like multiple caches or tables, if you will, you can have transactions that span a number of different caches. You can have optimistic or pessimistic modes. And of course, a bunch of different kind of isolation levels, like read repeated, repeatable reads, or serializable, and stuff like that. Based on some benchmarks, and some additions, I think it's about 50% faster in terms of transactions than most of the other stuff that's out there right now. Okay, so Java structure. I think I'll skip this slide. That's pretty much just saying there's the different features that we can use in Ignite in terms of the lower level stuff. So not only you have a distributed kind of map and queue, you have a set, you have a queue, you have a sequence that you can use, and a distributed executor service, right? So continuous queries. So we did say we can store the data in memory and we can access it, but actually what you can do is deploy a continuous query. So that's the ability to really create, let's say, different filters and evaluate based on those filters. So the idea is, let's say you're listening on specific data sets that are coming, in, and then you evaluate based on a certain filter, and then based on that, you trigger some business logic. So it could be like new business objects coming in that have a specific field, that has a specific, let's say, status, and then it says new. So what you can do is have a query that's listening, or a listener that picks this up and executes some business logic based on this input, right? The whole idea here is that you can create chains. So different continuous queries can create different kind of event chains and process it in a different kind of way. Of course, I'm trying to run through most of these things quite fast, and it's probably too early and a lot of information, but I'm just kind of conscious of time that we need to go. So we've got about 15 minutes to cover that. So that was pretty much the data grid, I would say, and that's kind of an overview. Of course, like I said, feel free to check out the documentation. This is a lot more rich than just those few features, right? Okay, so the compute grid. Very important, I think, how this kind of integrates together. But just a small gap before we go on there, streaming. So what's the perception of streaming in Ignite? That's the ability, like I said before, store data, but access it. And what you can do in terms of streaming is create what we call event windows. So that's the ability to define the eviction policies of your different data objects and then query against that event window. So imagine if these events coming in, they're clicks on the website, and you set the eviction policy of each of these events to 1 hour. What you can do then later is use a SQL query and query that and say, okay, give me the top 10 clicks for an hour. Because only in that sliding window, or that event window, we've only been dealing with that 1 hour, then that's where you will get your results based on that. If you want to do it over 3 hours, then you have to create another sliding window based on a 3-hour time frame, right? Okay, so clients and servers versus Affinity Colocation. So the new concept, I guess, here is Affinity Colocation, how that's different with what we currently do, I guess. So traditionally, if you see on the left-hand side, we have what we call the data nodes, so your database, and then a processing node. So traditionally, you would read data and then process it in the processing node, right? Heavy costs. I mean, if the data sets are big, you have to move a lot of data over the wire and then do the processing. What we can actually do is what we almost like a map reduce. I'm not sure if you're familiar with kind of HardOOP and that kind of paradigm or that idea. But the whole idea there is to send the job to the servers, to the processing nodes. Rather than reading the data, you send the processing to the data and you do that operation. Now, the easiest way to think about this is a map reduce, where you just broadcast, you work with a subset of the data, and then you read back. So imagine if those processing nodes and data nodes, at the same time, they hold the data, partition it, as we talked before about partitioning the cache, and now they process only individual subsets of the data. So it could be, for example, a change operation, right? So imagine I want to increase someone's salary or benefits by X amount, right? Usually you would have to read that, change it, and then write it again. What you can do is create a closure or a task or a job or a Java executable and then broadcast that to all the servers. Now what will happen is each server will perform that operation on the subset of the data that it's holding, right? And then give you the result back that you would get. Now, this gets more interesting because that's kind of a full broadcast, let's say, right? You can also be more specific in where you direct that processing. So, and that's what we call a data affinity access or affinity processing, right? What we didn't mention in the compute grid is in the data grid, when you partition the data, you can decide on which key you use to partition the data, yeah? So usually it can be the ID of an object. So object with ID 1 will end up on server 1, object with ID 2 ends up on server 2. Now, if you've got two different caches or two different entities that are related, right? Think person and address, right? So a person and his address are always related. I mean, okay, sometimes people might have the same address, but let's take for this instance that it's a one-to-one mapping. What you would do is insert the person with its ID and then insert the address with the affinity key of the person ID. So what that would guarantee is that the address object and the employee object or customer object will end up on the same physical node. So that means if you then want to do a join or process and say, okay, give me this person's address joined up, the request goes to the server that has the data, and then the data is served back. So that avoids kind of distributed calls around the grid where data is held everywhere. So the idea here is to have a strategy when you're splitting up your data, to split it up in a correct way across different entities that you position or collect them together or group them together with, as you would say, they had similar functions, right? It sounds simpler than it actually is, and it's certainly where it becomes difficult is not only when you're trying to partition the data, but also when you try to partition it and then try to think, how do you process that? So I think partitioning the data and having balanced clusters of partitioned data is okay. When you start to think about how you process that also in a balanced way, that's when complexity increases. So the merging of the compute grid and the data grid, very powerful, but can get very complex very fast, right? That said, the community and we are out there to help you and support you guys for all of this stuff. A cool little thing about the compute grid, which I didn't mention here, the whole idea is you execute closures or Java executables, right, or Java callables. That's just a piece of code that you can write, and then you can fire off to all the servers, to a specific server, or to a range of servers that they want to execute. This can be any piece of code, you know? It could be even restarting the server, it could be deleting all the data, it could be processing a part of the data, it could be anything. And what's cool about that is you got zero deployment. So that's the ability to spin up your cluster, write your task on the client side, and then fire it off to the grid without having to load the classes on the server side. We have what we call a distributed class loader. So as you fire the task, it gets distributed across the cluster. They all execute the task, and then the class is dumped. And you can have a new version of the same task, right? So really cool stuff, again, to kind of increase your momentum of development. The last kind of bit, I think, with the implementation of how it works is the in-memory service grid. So I think those are the most kind of important parts: data grid, compute grid, service grid, right? So service grid pretty much allows you to run within each of these process or nodes or deploy what we call a service implementation or a service instance, right? So that's pretty much a client has the interface and the server has the implementation. What this could be is actually you can deploy a service that exposes a number of different service calls and then makes a SQL call or a SQL API, use the SQL API to access the data, to access the cache. It can do some transactions. It can do some compute tasks. But the whole idea is that you're shielding or creating this service layer around this. Rather than giving access directly to the clients to operate against the grid, you can create your own services, similar to kind of exposing your own kind of API on top of it, right? The good thing about that is the resilience that you can add. So you can have a node singleton, what we call, so a service, the same service would be deployed on every single node. So as you increment the number of servers and you bring new nodes in, then this kind of automatically increases. The same way you can remove it. Or you can have a cluster singleton, which is one instance of this service running on the whole cluster. If you kill any of this service, or there's a problem with this node or this service, then we restart this node, right? And I think that's pretty much it. I'll try to run very quickly with the Hadoop stuff. So the idea here is that with Hadoop, what we provide is pretty much, if you've used it before, there's what we call a HardOOP Accelerator component to Ignite, which is basically allowing you to execute the MapReduce workloads or the jobs that you would execute before, but through Ignite without any code change. So what you do is you install Ignite, you configure Hadoop to work with it, just a configuration level, and then you can execute your old jobs, no problem. So that will speed up a lot of the stuff that since we're operating in memory, and of course, since we're using our own computational framework. But I think more interesting or more kind of popular nowadays is this kind of Spark integration, which is basically what we call in-memory shared RDDs. So that's using an Ignite cache as a shared RDD for Spark. So you can have Spark workers, each with Spark jobs. Now traditionally Spark would have its own RDD, but these are immutable and not visible to any of these other servers. If you use what we call an Ignite RDD, then you can make this available to all your jobs, to all your Spark jobs and all your workers in your cluster, right? And of course, you can speed it up with some in-memory indexes, like we said, with the SQL, and share the states across. So yeah, I mean, I guess JVM product or implementation can run anywhere. Pretty much that runs a JVM. The idea here in terms of cloud deployment and integration is the one bit to keep in mind is it can pretty much run anywhere, and we have support for most of these stacks. It's about discovery, right? When these nodes are going to come together and they need to discover together, it's about providing the right kind of infrastructure to do that. For example, in Amazon, we use S3 to do the node lookups, right? Because we don't have access to the network details. So, but anyway, the idea is that you can access or deploy Ignite to any of these kind of clouds, working on your own laptop, working in the same JVM, working on your own physical servers. The idea is commodity hardware running wherever you can. And I think that's pretty much it. It wasn't too much, but hopefully it was educating. Yeah.